Hi, I'd like to talk about Newton's laws as they apply more to the types of systems that Newton was studying when he wrote his Principia. And the specific system we're going to be taking a look at are the case of collisions. So let's pretend that we have a universe, a system that just has two objects, Object 1 and Object 2. Object 1 and Object 2 can both have a mass. They could both have an independent velocity v1 and v2, but since our system only has two objects, we could only have one interaction. Now Object 1 would say it's a force of 2 acting on Object 1. Object 2 says it's a force of Object 1 acting on Object 2, but from Newton's third law, really that's just saying that those are the same force viewed from two different perspectives. So the size would just be equal to minus, well, the size is the same, the direction's opposite, right? So if I were to add those two together, I would have to get 0 for the total force inside my system. Now if I were to apply the chapter 5 version of Newton's second law, that says that the net force acting on an object is its mass times its acceleration, well, the force of 2 acting on 1 would just be the mass of 1 times the acceleration of object 1. The force of 1 acting on 2 is the net force on object 2, which is the mass of 2 times the acceleration of object 2. I'm just carrying down this equals 0 to keep speaking in mathematical sentences. So, acceleration is a derivative. So, we could rewrite this as mass 1 times the derivative of velocity 1 plus mass 2 times the derivative of velocity 2, both of those derivatives with respect to time. Now, as long as we have constant mass and we're still in the universe of particles right now, so that's an okay assumption, and we aren't speaking relativistically yet. So I could distribute out that derivative. And that derivative then tells me that my derivative with respect to time of my quantity mass 1 times velocity 1 plus mass 2 times velocity 2 has to equal 0. And if you take a total derivative of something with respect to time and you get 0, you have a conserved physical quantity. And this actually leads us to a new way of expressing Newton's first law of motion. So the first law, remember we said, says in the absence of external forces, a quantity of motion is conserved. And Newton's quantity of motion wasn't the velocity, it's what we now call the momentum. And literally from Latin it translates quantity of motion. And the symbol we use for momentum is a lowercase letter p, and it's a vector because it's based off velocity, which is a vector. And the momentum is equal to the inertial mass of an object times its velocity. So, this old version of Newton's second law, we could do away with. Because if we take this idea and extend it one unit further, if we do have an external force, or many external forces, the sum of those external forces should change a quantity of motion, which means Newton's second law, more properly, is to say the sum of the external forces acting on an object or acting on a system is equal to the change in momentum of that object or system with respect to time. Thanks for watching.